Good morning, friends. Uh, Yesterday, as I have told you that we'll be talking today is the law of mass action. Law of mass action. This law is proposed by Cato M. Goldberg and Peter Wage. These are the two scientists, Norwegian scientists. Norwegian scientist in 1864 they have proposed this law. So let's write the law. But this law is very important law. The rate of any chemical reaction, rate of any chemical reaction is directly proportional, directly proportional, proportional to the product of molar concentration, molar concentration of each reactant molecule, each reactant molecule with with the power of with the power of each concentration, each molar concentration or each component, reacting component, each concentration, reactant molecule concentration, each concentration is is equal to the number of number of reactant reactant molecules molecules those are taking part in the reaction, those are taking part in the reaction, in the reaction. Although this law is very basic law, elementary law, nowadays this law is applicable only the elementary reaction, that is only single step reaction, but the law is very important one. Now the mathematical form of this law can be written, suppose a mole of A plus b mole of B, capital B, they are reacting together and they are forming the products. Now according to this definition, or the definition can be written like this: rate is directly proportional to molar concentration of each reactant molecule, each reactant product of molar concentration of each reactor molecule. In this case, A and B are the reactant molecule, raised to the power of their number of molecules or concentrations, right? Therefore A raised to small a and B raised to small b. Now this equation can be written: rate is equal to K into A to the power of small a, capital B to the power of small b, where K is called as rate constant. K is called as rate constant of the reaction. K is called as rate constant. Remember that, right? So, this limitations of this law is that what are the limitation of this law of mass action, that this law is applicable only only single step reaction step reaction. This law is not applicable to the multi-step reaction. But remember that this definition is very important. In the exam, they may ask the definition of the what is the law of mass action, right? Next, we will see the derivation of law of chemical equilibrium or chemical equilibrium. Next one is chemical equilibrium. Equilibrium. Now, let's consider the what we are learning. We are learning the chemical equilibrium. So we will be considering that law of mass action in the chemical equilibrium. Suppose in general reaction, we write generally general reaction A mole of A plus B mole of B, that gives forward reaction and backward reaction. Suppose this is the equilibrium reaction. We have learned the what are the equilibrium reaction, right? That can be go forward as well as backward direction. In the last lecture we have seen the what is the chemical equilibrium. So A mole of A plus B mole of B reacting together, they are forming C mole of capital C plus D mole of capital D, right? These are the product, these are the reactant, and in reversible reaction these are the reactant and these are the product, right? Therefore, according to the law of mass action, right now we have studied the law of mass action. According to the law of mass action, rate of forward reaction, forward reaction is equal to Kf into concentration of A raised to small a, concentration of B raised to small b. Forward reaction. We are in that case we are considering the this as the reactant forward reaction. This is the Kf and this is the Kr reverse reaction. Kr reversible reaction, right? Rate of backward reaction, rate of forward reaction means the product that are forming at the initial state. Rate of backward reaction, we can write Kr or reversible reaction, that is now this time this C capital C raised to small c and capital D raised to small d. Now this is the equilibrium reaction, right? This is the equilibrium reaction. At equilibrium, what is equilibrium? We have learned in the last lecture. At equilibrium, rate of forward reaction is equal to rate of backward reaction. Rate of forward reaction is equal to rate of backward reaction. Therefore, another constant comes out, Kc is equal to Kr divided by Kf is equal to Kr, that is C capital C raised to small c, capital D raised to small d, divided by capital A, that is reactant molecule of A raised to small a, and capital B raised to small b. This is called as the equilibrium constant, where Kc is called as equilibrium constant. Very important. equilibrium constant. Equilibrium constant. Kc is called as the equilibrium constant, right? Remember that at this kind of chemical equilibrium reaction we can calculate the Kc, that is equilibrium constant. Kc, how we can calculate? We can calculate from the law of mass action. What is the law of mass action? That we have learned some time before, right? Right. Now in thermodynamics, what is happening is that what happens is that they are not considering the concentration. In this reaction we have considered the concentration, barabar, concentration, right? Concentration we have considered, but in the thermodynamics they are considering as a activity. They are considering as a activity. Activity is what? If it is liquid, if it is liquid, what is liquid? If the reactant molecules are liquid, then its concentration ratio to the standard concentration is taken. Its concentration ratio to the standard concentration is taken if it is liquid. Means what? Standard concentration is what? 1 mole per liter is called as the standard concentration. Suppose A is the liquid, B is the liquid, right? A is the liquid and B is the liquid. This liquid that is reactant liquid. This liquid is how much concentration? That activity is taken. Activity, how it is taken? It is the ratio to the standard concentration. What is the standard concentration? 1 mole per liter. 1 mole per liter. Suppose this is the 2 molar concentration. 2 molar concentration. So the activity is taken 2 mole per liter divided by 1 mole per liter. 1 mole per liter. Why this is 1 mole per liter? This is the standard concentration. Standard concentration. Standard concentration is taken. Therefore, this comes out to be 2. Activity comes out to be 2. Since these are the units of this molar concentration as well as standard concentration are the same, therefore activity is the dimensionless quantity. Activity is the dimensionless quantity. Activity is dimensionless quantity. Now, if it is gas, the reactant molecules are gas. Suppose A plus B. A is gas and this A is gas and this B is also gas, and they are forming the product. Whatever product they are forming. While writing the rate of the reaction, or while writing the Kc, that is equilibrium constant, what we are considering? We are considering if it is the gas, then its coefficient is taken, activity is taken like this. Suppose it is the gas, the standard pressure, it is compared with the it is the ratio of standard pressure. How it is taken? Standard pressure 1 bar. Standard pressure is 1 bar, that is equal to 1 Pascal. 1 Pascal, that is equal to 0.9869 atmosphere. 9869 atmosphere. Then if the ideal mixture contains of the ideal gas or any gas contains, suppose some of the partial pressure, then X concentration of that partial pressure Px divided by P0. Px divided by P0 is what? Partial pressure of that gas divided by this standard pressure. Standard pressure is what? Standard pressure is 0.9869 atmosphere. 0.9869 atmosphere, and suppose that gas is having some of the pressure 0.5023 atmosphere is the that partial pressure of that gas in that mixture, whatever mixture is there here, the mixture is there, reacting molecule mixture is there. In that mixture, how much partial pressure exerted by that gas divided by standard pressure. Now this atmosphere get cancelled, again you will get the unitless quantity, dimensionless quantity, unitless quantity or dimensionless quantity, that is called as the activity. Activity is taken in the thermodynamics while writing the considering the reaction, while writing the rate equations in thermodynamics, they are considering the activity. How it is converted? Activity is converted divided by standard pressure, divided by standard concentration. If it is the liquid, standard concentration is how much? It is 1 mole per liter, and standard pressure is how much? It is 0.9869 atmosphere, or it is in 1 bar, or it is in 1 pascal. 1 bar or 1 pascal is equal to 0.9869 atmosphere, right? Remember that, this is very important. Now next, today we will be learning the types of the equilibria. The types of the equilibria. The types of the equilibria. Types of the equilibria. There are two types of the equilibria. Number one, homogeneous equilibria. Homogeneous equilibria. Homogeneous equilibria is what? It is the type of equilibrium reaction in which the both the reactant molecules as well as product molecules are in same phase. It is the reversible reaction in which it is the reversible reaction in which both the reactant molecules as well as the product molecules are in same phase. We know the phase is what? Solid, liquid, gas, and Bose-Einstein condensed state of matter. There are three phases of the matter, we know that. So in homogeneous equilibria, what is that? The reversible reaction in which reactant molecules as well as product molecules are same phase. For example, hydrolysis of ethyl acetate, methyl acetate, COO, CH3, it is in the liquid state, plus H2O, water molecule, it is in the liquid state. It is the equilibrium reaction in which, what is the product of this reaction? CH3COOH, that is acetic acid, plus methanol, CH3OH. This methanol is again in the liquid state. So these are the reactant molecule, they are in the liquid state. Reactant molecule, they are in the liquid state, and product molecule, they are in the liquid state. Therefore they are in the same phase, that is called as the homogeneous equilibria. For example, if you take the gaseous reaction, it is very famous reaction, nitrogen plus 3H2 hydrogen, these are in the gaseous state. What is the product of this reaction? Product of this reaction is ammonia, 2NH3. Ammonia, it is again in the gaseous state. Ammonia is the gas, this hydrogen is the gas, and nitrogen is the gas. All the reactant as well as product are in same phase. That is called as the homogeneous equilibria. Now you can easily define the definition of what? Definition of heterogeneous equilibria. heterogeneous equilibrium. It is a reversible reaction in which one of the reactant or product, they are in different phase, all are in different phase, they are in different phase, then that is called as the heterogeneous equilibria. Heterogeneous equilibria. For example, decomposition of sodium bicarbonate to Na2HCO3 that decomposes into what they will convert into Na2CO3. It is in the solid state, plus what is the product, CO2 gas plus H2O gas, and it is in the solid state. So this Na2HCO3, that is sodium bicarbonate, is in the solid state. This sodium carbonate is in the solid state, but the one of the byproduct or one of the product that is in the gaseous state, and this H2O is in the gaseous state. Such type of reactions are called as the heterogeneous equilibria. Such type of equilibria are called as the heterogeneous equilibria. Another example, calcium carbonate, CaCO3. What is the product of this reversible reaction? This calcium carbonate. Calcium carbonate is in the solid state. Calcium carbonate is in the solid state. What is the product of this reaction? Calcium oxide, CaO plus CO2. This CaO, calcium oxide, is in solid and CO2 is in the gaseous state. So reactant is in the solid state, that is in the different phase, and one of the product is in the different phase. Therefore such type of equilibria or such type of equilibrium reaction is called as the heterogeneous equilibria. Heterogeneous equilibria. In the next lecture we will see the next topic. Thank you. Bye bye.